So this lecture is about weak instruments and many instruments. And so I'll talk a bit about the motivation for this literature, which is largely sort of the recent interest. I mean, this is actually partly a very old literature going back to the 60s, but the recent interest really comes from one paper by Imbens and Kruger, where they had a lot of instruments, a lot of weak instruments, and they created a bunch of statistical econometric issues. So I'll talk a little bit about that and sort of what the issues were with that paper, and I'll talk a little bit about the recent theoretical literature on weak instruments, and as well as the literature on settings where there's many instruments. So by way of introduction, the standard normal asymptotic approximation to the sampling distribution for instrumental variables, the estimators, sort of including two-stage least squares and liminal, a whole bunch of others, relies very heavily on the fact that the instruments are actually relevant, that there's a non-zero correlation between the instrument and the endogenous regressors. Now, so if as long as that correlation is non-zero, then asymptotically, sort of using the standard asymptotics, where you let the number of observations get large and keep the parameters fixed, implies that you would get a limiting normal distribution and that the normal approximation would actually work. But if in fact this correlation is close to zero, those approximations may not be very accurate, even in fairly large samples. And so in the end, sort of the big, sort of surprising thing was that in this Imbens-Kruger example, even though they used census data with this, in particular they used a sample with about 300,000 observations, it turns out that the normal approximation still was very poor in that case. Now, I want to sort of make a sharp distinction in that, sort of in the subsequent literature, between the just identified case, or the case with low degrees of over-identification, but this is still true, but the normal approximation is still going to be very poor if the instrument is very weak. But it's not nearly as big. It's not nearly as big a problem in practice, even if the normal approximation is not particularly good. If you calculate the standard confidence intervals, even if they're based on asymptotic normality, which is not a good approximation, they will still tend to be fairly wide. And so even if they may not be completely accurate, it won't really matter, because you'll see that you're not learning anything from those data. Now, sort of in very special cases, and I'll be a little more, somewhat special cases, I'll be a bit more precise about that later. It could be that you could get informative and inferences and that two-stage least squares or liminal would have been misleading if applied. And so then there's some alternative methods available. But mostly those cases correspond to cases where the degree of endogeneity is so high that that those are not very relevant for most empirical work in cross sections. And so in the just identified case, I'm largely I'm going to discuss some of these alternatives that lead to more precise inferences. But there's not all that big a concern, because liminal two-stage least squares are essentially going to tell you that you're not learning much if the instruments are very weak. That's sort of very different from the case with a large degree of over-identification. And so part of what Imbens and Kruger did, I'll come back to that in some detail, but they used a large number of instruments by interacting their basic instrument, which was 3 indicators for quarter of birth. They interacted those with state dummies and year dummies, ending up with a couple of hundred, something like 180 instruments. And that turns out to have very strong implications for the quality of the normal approximation of two-stage least squares. So in that case, two-stage least squares is very biased towards OLS, and the conventional two-stage least square standard errors are very substantially underestimate the precision, or substantially underestimate the variance of the standard errors. Limmel is much better in that case. It's still centered pretty much at the true value, other than when the instrument is completely irrelevant, obviously, because then we're just dividing something by zero and sort of not really clear what then the estimator couldn't possibly be centered at the true value. But if the correlation is not completely zero, Limmel still tends to be centered at the true value. But if the degree of over-identification is very high, its standard error is not correct. And so in the end, there's some very important and sort of not always appreciated work by Paul Becker, deriving asymptotic distribution that allows the number of instruments to increase with the sample size. And that suggests, sort of in the simple case where there's just a single endogenous regressor, a very simple adjustment to the Limmel standard errors, a multiplicative adjustment that is just based on the correlation, sort of on the explanatory power of the instruments, and that actually works pretty well. So overall, pretty much irrespective of whether there's any concern about the weakness of the instruments, there's no reason to use two-stage least squares. Sort of if in the just identified case, obviously it's the same as Limmel, but in cases where there's any over-identification, I know of no systematic reason why you would use two-stage least squares rather than Limmel. And moreover, if you're using Limmel, I would generally be inclined to apply that adjustment from Becker's work, sort of, which also relates sort of to random effects specification. I would apply that adjustment to the Limmel standard errors, because if in fact the instruments are not weak, that adjustment will just vanish and won't make any difference. But it would generally make inferences much more robust, sort of in a systematic way. And part of the attraction of that adjustment is that sort of under these Becker asymptotics, you still get asymptotic normality. So all the standard methods about the standard interpretation of confidence intervals are still going to work. And the relation with the random effects interpretation suggests that, in fact, you can also still interpret these confidence intervals as Bayesian probability intervals. So here, I would sort of actually I would have fairly strong recommendations. I would just never use the two-stage least squares. I would always use Limmel, but adjust the standard errors in this relatively straightforward way. Okay, so let me start at the Angus-Kruger paper. I'm sure lots of people have seen that paper. They were interested in estimating the returns to education. They were concerned with endogeneity of the years of education. So they thought of exploiting variation in schooling levels coming from compulsory schooling laws. So compulsory schooling laws affect people differently depending on when they're born. So with the idea that if you're born before October 1st, you would go to school a year earlier, almost a year earlier than people born after October 1st, if the October 1st is the cutoff date. And so perhaps somewhat surprisingly, that actually leads to variation in average education levels by quarter of birth. Imbens and Kruger then decided to use the indicator there for quarter of birth as an instrument. There may very well be some issues with the validity of that. For example, there could be concerns that starting the formal education early at a younger age may have differential impacts. So you should go back to that paper and kind of look at all the concerns they raise and why they think they may or may not be relevant. That's not the topic I want to discuss here. But given that they use quarter of birth, if they just use here I just did a very simple version of that, using only data from the first and fourth quarter. So then the IV estimator, which is the same as two-stage least squares, which is the same as limal, it's just the ratio of, within the numerator, the difference in average earnings for people born in the fourth minus average earnings for people born in the first quarter, divided by the difference in average levels of education for those groups. You do that, and so using asymptotic normality, using the delta method, for the standard errors, you get a point estimate of 8.9% with a standard error of 1.1, and so that's all fine. There's no serious problem with this. The effect of the quarter of birth, or the correlation between quarter of birth and years of education, is small, but with 300,000 observations, it's very precisely estimated, and asymptotic normality here is not an issue. So the issues arise sort of in some of the later estimates where they interact the 3 quarter of birth dummies with 50 states of birth and 9 year of birth dummies in order to try to get more precise estimates sort of based on the conventional wisdom and the correct wisdom based on first order asymptotics, that by having additional instruments, you would not hurt your estimates, but you could potentially get more precise estimates by soaking up additional variation. Here, I'll look at some estimates, and sort of instead of just interacting with these 50 state and 9 year of birth dummies, I actually interacted it with state times year of birth dummies to get 500 instruments to make some of these comparisons a little starker. So with also these state times year of birth dummies as exogenous variables, so they had a linear instrumental variable set up with these 500 instruments uncorrelated with the unobserved component in the regression function. And we're still interested just in this one coefficient, years of education. That sort of, if you do that, if you look at the two-stage least squares estimates, that looks fine. In fact, sort of that looks as if it justifies getting these interactions. You see, if you compare the estimate to the one here we get standard error of 1.1%. Here, using two-stage least squares, you get a standard error of 0.8%. Maybe that's not a big deal, but certainly it doesn't seem to hurt you. There's nothing in the two-stage least squares estimates that really raises any that would seem to raise any concerns. Now, if you do limal, so that you get a slightly different picture. In fact, the standard error there goes up from using all those additional estimates, as well as being surprisingly different from the two-stage least squares estimate. But if you just look at the two-stage least squares estimate, and I remember when Imbens and Kruger were doing some of this stuff, seeing these estimates, and certainly nothing would have suggest to me that there was a problem here. But it turned out there was. And so there's a very clever paper by Bound, Jaeger, and Baker. And so the implication of that is that despite the fact that, that Angus and Kruger have huge samples, these asymptotic normal approximations may not work very well because the instruments are only very weakly correlated with the endogenous regressor. And so the most striking way of, the most compelling way of seeing that is based on the following idea. If you take the Angus-Kruger data and redo these calculations after taking out the actual quarter of birth dummies, but just replacing them with random binary indicators with the exact same marginal distribution, and then see what these estimates and the standard errors look like. Now, in principle, what you would like, sort of, obviously, if you do that, there's no information in the instrument. It's completely random. You're trying to estimate a ratio of population covariances, both of which are 0. And so you would like, sort of, there's no particular reason to expect it to be centered in a particular place, but you'd certainly like the standard error there to be big. And asymptotically, it should be big because it somewhere in the standard error appears the square of is 1 over the denominator, which is 0. In principle, sort of that's what you would expect, that you would hope to find, even though in principle the normal approximation obviously wouldn't work because you're dividing two things, you're dividing two objects, both of which are estimating 0, and so for both the numerator and the denominator, the normal approximation works fairly well. But so you would get a Cauchy random variable rather than a normal random variable. But in principle, that shouldn't be necessarily give you that big a problem. You would expect to just still find a fairly wide confidence interval. But the surprising thing from the Barnjager paper is that if you do that, not so much with the single instrument, where sort of I report these numbers here for the data I was using for these earlier calculations. If you do this for the single instrument case, now you get an estimate of the returns to education of minus 196%, so obviously a ridiculous number, but you also get a very large standard error, so there's no particular concern with that. If the instrument had been so weak, had been completely uncorrelated with the years of education, getting a number like this would not have misled anyone into believing that they were learning something. But the concern is in the case with the 500 instruments. Even if these instruments are completely random, two-stage least squares looks as if it's giving you a very precise estimate, as well as a very, looks like a very reasonable estimate. Here, the point estimate is 5.9 with a standard error of 0.9%. And so that's really the basis for this whole subsequent literature. Because if you did this without being aware of this problem, if in fact you had instruments that were completely uncorrelated with anything, you might still have got the numbers that you would be willing to report and that look very reasonable. And so that's obviously not a great thing. So the subsequent literature kind of set out to try to understand that and come up with better procedures. Now in this case, already you can see that Limmel does much better. Limmel gives you a nonsensical point estimate here of minus 33% for the returns to an initial year of education. So it would have been very unlikely that number would have been taken very seriously. But it's still a bit of a concern that the standard error is actually 0.1 here, suggesting that this estimate is actually relatively precise. So even though Limmel doesn't do nearly as bad as two-stage least squares, its standard error here is 10 times that of the two-stage least squares one, it's still not doing particularly well. So in order to So in order to illustrate that problem a little further, I did some simulations to investigate particular aspects of this. And so what I did here was take 10,000 artificial data sets, all of the same size as this subset of the Angus-Kruger data that I was using, 160,000. In each case, half of the individuals would have quarter of birth equal to 0, half would have quarter of birth equal to 1. I sampled reduced form disturbances from a joint normal distribution centered at 0 with marginal variances equal to the variances estimated on the Angus-Kruger data, and correlations and I'm going to play around with the correlation there, with the correlation equal to rho. Then I sort of randomly drew years of education and log earnings using a linear model estimated on the Angus-Kruger data. So education is equal to 12.688 plus 0.151 times quarter of birth plus this normal term. So these data are just going to look like the Angus-Kruger data, other than they're continuous, they're normally distributed, but that isn't really the issue. With the 160,000 observations, asymptotic normality is perfect for simple objects like averages. It's going to be perfectly fine. It's all going to come off the concern about the ratio of these things, but it allows us to focus on what are the determinants of this problem. And so what I then did was for each of these 10,000 data sets, calculated the standard IV estimator and its standard error, either using the actual quarter of birth or the random quarter of birth variable as the instrument. And what I was interested in was how misleading standard inference would have been in all of these cases. And the one thing I'm going to vary across some of these experiments is the correlation between the reduced form errors, which essentially amounts to varying the degree of endogeneity. And so the test is just going to be the standard, sort of based on t statistic. I would reject the null if the ratio of the point estimate minus the truth, which is 0.089 here, and the divided by the standard error is is greater than 1.96. So I did this for a bunch of different values of the reduced form error correlation. And so here in this table, sort of based on these, for each column, this is 10,000 data sets. Look at the coverage rate for these confidence intervals, as well as the width of the confidence interval. So both the median width and the 0.1 quantile. And so what you would be concerned with is if you use the random quarter of birth, if the coverage rate was low, as well as if the width of the confidence interval was small. And so here we can interpret these numbers somewhat substantively. We know the returns to education are somewhere between 0 and 20% per year. I think so. There's people here who know more about this than I do, but I think most people would agree that it's probably somewhere between 0 and 0.2, certainly given the Mansky bounds we saw yesterday. So that's sort of the perspective I'm going to put these numbers in. If we do this for the real quarter of birth data, the fact that you have 160,000 observations, this gives you accurate estimates, accurate confidence intervals. Confidence intervals have 95% coverage, irrespective of the degree of endogeneity. If you use the random quarter of birth, you actually have coverage rate much higher than 95% for most of the values of rho. It's only when you get to values of rho that are extremely high, sort of 0.9 and higher, especially by the time you get to 0.99, that the coverage rate goes below the nominal one. Even in that case, the median width of the confidence interval is still pretty high, But now now occasionally you'll get confidence intervals that are much narrower. But the point I want to make here, and I think this is not always been very clear in some of the theoretical literature, is that in a case with just identification, even though normality doesn't necessarily hold, you need arguably unrealistically high degree of endogeneity before standard confidence intervals would really be misleading. You may not get a confidence interval that has the right coverage rate, but it's not going to suggest that you get a precise estimate of something when in fact you're not learning anything from the data. And so, let me relate this to some of the technical literature. So one way of describing this problem is that conventional confidence intervals, confidence intervals based on a point estimate plus 1.96 times the standard error. These conventional intervals cannot be valid uniformly over the parameter space. There's going to be parts of the parameter space where those are going to have coverage that is much lower than the nominal ones. And that's been established theoretically. There's some work by Dufour, some work in the statistical literature that it's not possible to construct confidence intervals that are valid uniformly if these confidence intervals are of the form standard point estimate plus 1.96 times the standard error. However, that doesn't mean these things are going to be particularly misleading. We may not care about all parts of the parameter space equally much. And in practice, I think in the just identified case, I have not seen any examples where the standard inference would have been substantially misleading. Now, that is in sharp contrast to the case with many instruments, where, as the simple example based on the Angus-Kruger data already showed, that inference would have been misleading. And there really is a concern, and I think now you should not, people probably would not, but certainly should not do two-stage least squares and completely ignore these problems. Okay, but let me still pursue the single the just identified case. I'm only going to look at a case with a single endogenous regressor. So this will be a single instrument, single endogenous regressor case. Let me pursue that case a little further, kind of to get an understanding of what can be done and what effect that will have. So the setup here is just linear model for Y in terms of the endogenous regressor, linear model for the endogenous regressor in terms of the instrument, single instrument. We're going to use asymptotic normality, and that's not where the issues are. You could, especially if you have reasonably large samples, normality for the errors doesn't really make all that much difference. Reduced form for Y in terms of C is also there. The parameter we're interested in is this ratio of these reduced form coefficients. Omega is the reduced form covariance matrix. So in most of the theoretical literature, that's actually taken as known, because that simplifies the theoretical calculations enormously. That's not a big deal in practice either, because with a reasonably large sample, you can estimate that well. It's very different from the covariance matrix of the structural errors, because that's very hard to estimate, because that actually relates directly to the degree of endogeneity. But the reduced form covariance matrix is easy to estimate. So in this case, the standard IV estimator is just this ratio of sample covariances. And one other object that is going to be important here is what is known as the concentration parameter, square of the reduced form coefficient times the sum of the squared deviations of the instrument from its mean, scaled by the reduced form variance. And so another way of saying that the instrument is weak is that the concentration parameter is small. If in fact the sort of pi1 differs from 0, then in large enough samples, this concentration parameter goes to infinity, and everything's going to be fine. But in finite samples, lambda may be relatively small, even if pi is not completely equal to 0. And so, two more kind of preliminary things. So if you just look at the numerator and the denominator separately, we're essentially thinking about cases where both of those separately, or in fact even jointly, are well approximated by normal distribution. It's not that there's any concern that the denominator itself is not normally distributed. The concern is going to be that the denominator is just small, and that therefore the ratio is not well approximated by by a normal distribution. So if the denominator is centered away from 0, you could just use the delta method. But now the derivative in that delta method formula is gets very large, and we get a distribution that is much better approximated by a Cauchy distribution. Now, sort of how can we think about this? So one way that's been suggested by Staiger and Stock is to look at the distribution of the standard IV estimator under an approximation that sort of focuses on the weakness of the instrument. And so instead of doing this under asymptotics where the sample size gets large and we have a fixed set of parameters, they approximate this the distribution of the IV estimator as if the instrument is going to 0, implying that the concentration parameter converges to a constant. And so in order to interpret the behavior of some of the standard confidence intervals, the Staiger and Stock look at the coverage properties of those confidence intervals under this particular sequence. Now, in some sense, that is sort of the relevance of that approach is not so much whether that particular asymptotic sequence is the most interesting one. So what the key insight from that is that it shows so that if you get a difference between the coverage rates under that sequence than for the standard asymptotics, then it implies that there's values of these pi's such that standard confidence intervals are going to have coverage that is substantially away from the nominal coverage. And so really, sort of another way of thinking about it, and that's sort of in line with some of the very recent work, is to think of standard confidence intervals not having coverage uniformly in the parameter space. Now, as I said before, we may not care about uniform coverage everywhere, but you can argue that we may, that at least in some cases, we want uniform coverage over a particular part of the parameter space. And here, we can think about looking for methods that have uniform coverage around the area where pi is equal to 0. And so some recent work by Anna Mikosheva looking at these weak instrument problems from that perspective. Now, you can sort of only do that for confidence intervals. You can't do that for estimators, because if pi1 is equal to 0, there is not going to be any good estimators. But you can, in fact, find confidence intervals that work well here, even if pi is equal to 0. So the next thing I want to do is look at some of these proposals for confidence intervals that work well uniformly around pi is 1. And so, I mean, this is sort of partly because there's certainly cases where this is useful, although with some reservations that I think for this just identified case, standard confidence intervals are very, very rarely going to be very misleading, but it'll also lead into case with multiple weak instruments. So for the just identified case, the sort of very clear way of getting a confidence interval that is valid uniformly in the parameter space. This is based on work by Anderson and Rubin. And really, the key paper is 1949. The remarkable thing is that Anderson is still actively writing things and doing things. A couple of years ago, I had it's not always the most interesting work he's doing. A couple of years ago, he had a paper showing that, and this was for a fast-drift for tile. He showed that in fact it wasn't tile, but Anderson who had come up with two-stage least squares. It seemed a remarkable thing to be doing sort of by the time you're in your 90s, especially given that in the current literature, two-stage least squares is probably something nobody should be doing, and so it's not clear why you would want to claim credit for that. But this 49 paper is a remarkable paper, really, and sort of has some very useful results in it. So the idea is that so take the instrument deviations from its mean, look at the statistic, look at the correlation between the instrument and the deviation of the outcome, the difference between the outcome minus beta times xi, as a function, and look at that statistic as a function of beta 1. If you have the true value of beta 1, you should have something that you should have two objects that are uncorrelated. They should have mean 0, and in fact conditional on the instruments. And, this is just a product of C and the residual, so it would have an exact normal distribution. So if you have the correct value of beta plugged into that statistic, you get something that has an exact normal distribution. Then you can use that for testing the null hypothesis that beta is equal to beta naught. And in the end, you can base a confidence interval on the set of values of beta that don't get rejected by this test. And the test is an exact test. And if you assume the epsilons have a normal distribution, then irrespective of the power of the instrument, irrespective of the reduced form coefficient pi 1, this statistic is going to have a chi-squared distribution. And so the confidence interval on this is going to have the right coverage, irrespective of the value of pi 1. Now, if in fact pi 1 is close to 0, this is obviously not a very powerful test because there is not going to be any power to any test. And then you may this confidence interval can be equal to the whole real line. That's sort of in some sense as it should be in that case because there's just no information in the data. Now, if we, and this sort of gets closer to the case with many instruments, but suppose we do this in the over-identified case with just a few instruments, you can still do exactly the same. You can still look at the statistic, which is now a normally distributed vector rather than a scalar. You have a quadratic form in that is going to have a chi-squared distribution. That's all fine. But the problem is, if you try to base a confidence interval on this, it may be that in fact the confidence interval is empty for a particular data set. Even if the model is correctly specified, it may well be that there's no value of beta that is in that confidence interval, that is in that confidence set. And so I referred to that earlier yesterday when I was discussing Bayesian methods. I find it extremely objectionable to have procedures that sort of under the correct specification could actually lead to confidence intervals that are empty. That to me seems a somewhat meaningless exercise. And it suggests really that this is not a good way of constructing confidence intervals in this case. Now, note this cannot happen in the just identified case. There, the IV estimate itself is always going to be in the confidence set. this really is something coming from the degree of over-identification. And it's a problem that gets much worse if we have many instruments. At that point, 5% of the time, you're going to have an empty confidence set. And so it's not that let me be clear, it's not that the confidence interval is not valid in that sense. It does give you coverage 95% of the time, but it'll in the end look like 95% of the time you get the whole real line, and 5% of the time you get nothing. And that does include the truth 95% of the time. It just isn't very informative. Now, so there's been a number of ways of addressing that problem. One is a suggestion by Frank Kleibergen to modify the Anderson-Rubin statistic. Instead of looking at the correlation between the instruments and the residual, he looks at the linear combination of the instruments using the estimated first stage coefficient. That is essentially looking at the correlation between the residuals and a single instrument. And even though there's this estimated pi in there, that doesn't really matter for the asymptotic distribution. We lose exactness, but you get an approximate chi-square 1 distribution. And you can use that to construct a confidence interval, and that's going to be valid asymptotically, uniformly in the parameter space. Then there's some work by Moreira, who's focused on improving these tests, sort of, and the key idea, sort of a technical notion that's called similarity, where you want to ensure that tests have the same rejection probability for all values of the nuisance parameter, which in this case is the pi's, by adjusting the critical values. So think back about Kleibergen's statistic, which would have a chi-squared distribution. If you want to make this into a similar test, you would adjust the critical values in a way that asymptotically they would look like chi-squared quantiles, but in finite samples they would give you better coverage. And so another place you could do this is by using a likelihood ratio test and adjust the critical values there. So it looks somewhat more complicated than it actually is, and Moreira has programmed this up in Staiger. So I think actually on his website you can find a link to the Staiger program and implement this. Final comment on the just identified case, or the sort of the case with low degrees of over-identification, and that's sort of a more conceptual point, but sort of somewhat of a concern. All these confidence intervals, and what these confidence intervals set out to do is be valid uniformly over the parameter space, uniformly with respect to the value of pi 1. They achieved that goal, but part of that means that it's not valid conditional on the first stage. And so what do I mean by that? So suppose what you actually do is do the first stage, look at the coefficient, look at the F statistic there, and then if you see that the first stage is very weak, you decide to just abandon the project and do something else, and only continue with the second stage if you get a sufficiently high F statistic. Then the large sample coverage probabilities wouldn't be the same as the nominal ones. Now, so the question then is, what do people actually do in practice? And my guess is sort of partly judging from the Angus and Kruger paper, where they spent sort of, I think about 5 pages discussing the first stage, partly to substantiate their argument that sort of there is validity to their story that compulsory schooling laws affected average education levels. And I think sort of in a very sensible way, where you have a theory why the instrument should actually affect the endogenous regressor. And so part of the analysis involves checking whether that story is consistent with the data. But if you do that, then in these weak instrument problems cases, you would still have a problem with these alternative confidence intervals. Now, there's been some work developing methods that would be valid conditional on the first states. And there's some very interesting work by Laura Kyoto and Michael Jensen that is still sort of somewhat difficult to apply, I think. But it's, I mean, I want to raise that here as a concern that it's not always easy to. There is still some concern with these confidence intervals. Okay, the last part on many weak instruments. So here, this is in my view actually the most serious concern with these weak instruments. So I showed earlier the example of two-stage least squares with completely irrelevant instruments leading to what look like precise estimates far away from zero. So the first point is that there's no simple fix. Sort of a simple fix like bootstrapping doesn't work. If in fact you look at bootstrap standard errors, they're very similar to what two-stage least square standard errors give you. In this case, the theoretical literature has gone a couple of different directions. Some of the literature has focused on getting better inferences, better standard errors for conventional estimators or alternative confidence intervals. And in addition, there's a whole bunch of new estimators. People have looked at various members of the K-class estimators. There's various versions of Fuller estimators, bias-corrected versions of that. So I was thinking about what to say about it. I was talking to Jeff about that. And so he told me the story that when he was in graduate school, Rob Engel asked at some point in his econometrics class, have you guys heard of the K-class? And so when nobody said yes, he said, well, now you have. And then he moved on. And so I think this is sort of one of these cases where there's many more estimators in the theoretical literature than have been used in the applied literature. And I don't really see a lot of reason why that should change. Sort of here, I think sort of the most important results for this case, sort of one of the most important results is this Becker, is from this Becker paper. So Becker derives sort of formal large sample approximations for some of the standard estimators, in particular two-stage least squares and Limmel. And so where he lets the number of instruments increase proportionally to the sample size. So K, the number of instruments here is assumed to be equal to alpha times the sample size. It shows that under that sequence, two-stage least squares is not consistent. And that's sort of really, that's one way of demonstrating why two-stage least squares is going to have poor properties. What is more remarkable in a sense is that Limmel is consistent in that case. But moreover, he shows that the conventional Limmel standard errors are not valid. And he derives a correction to that based on that asymptotic sequence. And it turns out even with a relatively small number of instruments, that adjustment can be substantial. And so here, in the paper, there's sort of a more complicated version of these standard errors. But if you simplify this to the case where it's just a single endogenous regressor, in the end, what the adjustment looks like is something like this. Obviously, this depends on a bunch of unknown parameters. The coefficient of interest is in here, beta 1. The reduced form variance-covariance matrix, omega is in here. But using estimated versions of these things gives you an adjustment that I think in practice actually takes care of most of the problems with Limmel and would substantially improve the properties the associated confidence intervals. You can sort of see what can go wrong here. There's a couple of components to this adjustment factor. There's the number of instruments itself. Even if the number of instruments is relatively small, if that ratio to the sample size is relatively small, it can still be large if one of two things happens. One is if the power of the instruments is very small. If the sum of the pi prime z squared is very small. Second thing that can happen is if this last factor is close to the before you take the inverse, if that last factor is close to 0. And that can happen if you have very large degrees of endogeneity. So that's sort of where the dependence on the degree of endogeneity comes in. But so even if the instruments are not weak, putting in this adjustment factor is not going to affect things all that much, because at that point the adjustment would be very minor. So this is something I would actually seriously recommend people to do in practice. So irrespective of the number of instruments, use limal rather than two-stage least squares, and calculate this adjustment factor, and either use those standard errors, or sort of, if you find that the adjustment factor is big, you may want to go further, but certainly that would safeguard you against a lot of trouble. So there's another way of motivating some of sort of part of the Becker adjustment. So I talked a little bit about this work with Chamberlain in the Bayesian part, but sort of we looked at modeling, looking at this problem by modeling the reduced form coefficients as coming from a random effects specification. So, so just setting this up, so assuming the pi's come from a normal distribution with mean mu pi variance sigma squared pi, you can just get the likelihood function, and now this, in contrast to the likelihood function in terms of the original large parameter space, now there's a likelihood function with relatively few parameters. This is likely to work to be much better behaved in terms of being able to approximate it by a quadratic function. The quadratic approximation is much more likely to be accurate in terms of inferences. And so the interesting thing is that if you look at this random effect specification, if you look at this likelihood function based on the random effect specification, if you fix the variance of the first stage coefficients, if you fix sigma pi squared at a large value, the resulting, sort of the concentrated maximum likelihood estimator for beta 1 turns out to essentially be two-stage least squares. So implicitly, two-stage least squares is based on the presumption that the first stage coefficients collectively are very important, are far from 0, that their variance is large. And so I interpreted it yesterday from a Bayesian perspective as saying that two-stage least squares puts a lot of prior mass on this variance of the first stage coefficients being large, despite the fact that what we're actually concerned with is that these first stage coefficients are all very small. Now, if in fact you use another special case of this random effects estimator, and you fix the mean of that random effects distribution at 0, you assume omega is known, then we show that the random effects, so this random effects Quasar maximum likelihood estimator is in fact identical to limal. But again, just like the Becker analysis, the random effects calculation suggests that the conventional limal standard errors are too small, and it suggests adjustment that is very similar to the Becker adjustment, other than it replaces sort of the average squared parts of the first stage by an estimate of sigma pi squared. And so that'll tend to be, the latter will tend to be smaller. And so the adjustment we suggested is actually ends up being even bigger than the Becker one, even though that's probably less important than the fact that it's being adjusted at all. So the two more points. So the very different approach, it's a very interesting approach by Donald and Newey. They look at the question of choosing a subset of the instruments. So and the way they formalize that is by setting up a sequence of instruments and deciding where to cut things off. So instead of using all the 180 instruments, if you're willing to order them, you could imagine that you decide that using all 180 of them is not an attractive option, but you may want to use more than just the first three. And so they suggest a procedure for deciding how many instruments to use based on an approximation to the expected squared error of the estimator. That's sort of a very general idea and one that's sort of very promising in other settings as well. For example, in settings where you have in generalized method of moments settings with many moments, but it's sort of still somewhat difficult to actually implement. Okay, finally, so how much evidence is there of how well these things work? Sort of very extensive set of simulations done by Alfonso Flores, where he compares a whole bunch of these estimators, some of the ones that I mentioned before as never really having been used. But in fact, he doesn't include the limal with the Becker standard errors, which is one that probably should have been included in there as well. So he looks at coverage rate and bias, and he finds that this random effects estimator works very well. But in the cases he looks at, it's going to be it's generally very close to limal. But in the simulations, it has a much better standard error because it has essentially this adjusted standard error where the limal version that Flores uses has the conventional standard errors, and they're far too small, even in the settings that Flores looks at. Okay, so again, let me stress the point that in practice, I think it's sort of very clear that if you're using a lot of instruments, you don't want to use two-stage least squares. And in my view, there's pretty much no reason to use two-stage least squares rather than limal, other than in the just identified case where they're the same. And that if you do have over-identification, I would encourage people to adjust the limal standard errors, and sort of the simplest way of doing that is just using that Becker adjustment. Yes?
Question about the Becker adjustment. You said that the Becker adjustment there are some things that you do not know.
Yes.
So I'm a little confused. Is that the same thing as saying you don't know the inner term?
No. So you would just plug in the estimated values here. So here first you get the point estimate, you get beta hat, you get the estimate for the reduced form variance covariance, and you just plug that in here. So the only two components you don't know here are beta 1 and omega, and you just plug those in into that formula. And so I don't think that affects the properties of the confidence intervals very much.